So welcome everybody to our today's presentation. I will talk about the nonlinear multiscale modeling for short fiber reinforced plastics with Digimat software. And what I have brought to you today is an overview. Here we see what we'll be covering. So first we start a little bit in Extrem engineering, not only what is the company about, but also what is our strategy towards multiscale modeling. We look into depth a little bit into the material properties of short fiber reinforced plastics, and then we will see how we cover these properties by material modeling approaches. And then we will proceed with a view on how to incorporate these material modeling technology into different types of simulation strategies. And we will see some application examples of these strategies, of course. Then, in the end, we will cover also the topic of fatigue, which is a very researchy topic, I would say, for short fiber reinforced plastics, but where we have like heavy activity pointing towards future approaches in modeling. And then we will finalize by a quick view into the different modules of the Digimat software itself, and we will have a brief summary. Okay, so let's start by Extrem engineering and the multi-scale modeling strategy that we use. Extrem engineering, it's well known now. We're an MSC Software Company, but even though we have been acquired by MSC by the end of last year, we're still an independent company in the sense that we remain the team that we have been before. And you can see on the bottom of this slide a nice picture from our last year's users meeting in October 2012 in Amsterdam. And this is basically who we are. We are a team of experts, and most of them have a PhD degree in micromechanics or some applied field in that direction. And what we basically do is that we create a lot of technology and application around composite materials. And when we talk about composite materials and the challenges associated with them, it's really about the interdependencies in the design of a composite part that we are concerned with. So interdependencies, what do I mean if I say that? It's really that the part performance is not purely coming from some kind of average material property that you define on a part, which geometry you have drawn in some CAD tool, and then you put it to your FEA software. Now, for composite materials, it is that material properties are locally differently distributed over your part. And this is because the processing influences locally the arrangement of the underlying microstructure in your material. This tweaks the material properties, in the simplest case, the stiffness of the property, but also the failure of the property, so on and so forth. And this, again, will influence the part performance. And so we say if you want to really design a composite part, it is necessary to go for a coupled analysis where you really base on the process itself. You take into account locally the impact of the process on the material property. This will be fed into a computation of the part performance on the FEA side, and this way you get the most accurate results, and it's really like realistic, and processing material and part performance cannot separately be discussed any longer, but it's really one overall approach. This is how we see it and how we approach it is by multiscale modeling. And multiscale modeling for us really starts at the microscopic level. So it's for the material really that for the short fibers we start on the microstructure itself. So the material itself for us is a simulation model. And we gain a lot of highly detailed insight on this level about stresses and strains and so on in the material. But then in the end, when we turn to a material model, so this is what you see on the right side of this slide, what you will have is an average description for this kind of local material and local microstructure. And the Digimat material model is sensitive to the fiber orientation. And this is what you see here. You tweak the fiber orientation and you get different curves, different stiffnesses for each individual orientation of the fibers. And basically what you get, and this is indicated by the two red curves, is a large spread of material properties. And this is exactly what we do. We distribute now these different properties over the part based on the information that we get from a processing software. So with this overall approach, you can now go from the microscopic level, where things are defined, onto the macroscopic level. And the first level that you typically look into is the level of the dumbbells. So you perform or you do a validation of your approach, of course, in comparison with the experiments that you have done for dumbbells. And what you see here is, for example, the failure on the dumbbell, and you nicely see a distribution in terms of a skin core effect, and this is exactly an effect you get when you cut out a dumbbell from an injection molded plate. So it's quite realistic what we compute here, and then we go to the next level, which is the part level of the design. And here, again, we take into account the processing of the part, we put that to the part performance. And the final step that you can go is that you lift this kind of general approach up to the system level, so to the full car crash level, for example, in the automotive industry. And here we have seen recent results which really nicely see that we have arrived there. So we had a presentation from JSOL on our October users meeting showing a full car crash level simulation with 3.1 million elements, incorporating an injection molding part for the bumper beam. And we will look into that example later on a little bit more into detail. So this is our generic approach, and we even cover like new topics. So new topic for us in terms of short fiber reinforced plastics could be MSC, so the foaming of the material matrix, and we take exactly the same approach. So we start with representation of the microstructure to understand the material better, the mechanisms in the material. We derive a material model, and here the material model is a multi-dimensional one. So it's not only sensitive to the fiber orientation, but at the same time to the amount of voids in the matrix. So this can be locally distributed in the MSC process as well. Then we turn towards the validation on dumbbell level. Here we have limited results, I would say, up to now, but we are in direct customer contact investigating that further. And then we go to the part level, map the results from processing, and again, compute the part performance. Basically, in this slide, I want to show you that the approach that we take to modeling, to multiscale modeling, is always generic, and whatever kind of composite material we want to compute, we will follow this approach with the complementary technologies on the micro level, like in-depth computation of the material itself and the representation of the material in terms of a material model, which is anisotropic. Okay, so this brings us to short fiber reinforced plastics as a material. And if we look at the material and we look at some injection molded plate, it becomes quite quickly obvious why short fiber reinforced plastics is really complex in terms of describing the composite material. This is because you will have a distribution of your microstructure in the material. So if you cut the plate and you look across the thickness, you will have different layers of different orientation of fibers, so complex underlying microstructure. And if you now cut out a dumbbell inflow direction from this plate and you measure it, you will get something with a high stiffness because mainly the fibers have some state of high alignment, so you measure along the fiber. If you now do the same and you cut out something transverse to the fibers, it's exactly the opposite. You go transversal to all these fibers in your material, and this is the weakest possible state that you can have for this material, and this will result in a low stiffness. And so this is the situation that you have. And now you can think about the consequence on the level of the part, and here we have some artificial test plate that we created for understanding or for reducing this discussion to 2 dimensions. And I'd like you to take a look at the movie here of the filling. So here we go. You'll see that we come in with a mold front. The mold front hits some barriers. And basically what we create in this scenario is that we induce flow lines first and then static weld lines in different local areas of this plate. So we can take a look at the fiber orientation as on this slide, and again we come in with a fully aligned flow. We hit the barriers. What it creates is flow lines, so you have a change of highly aligned fibers in this 2D example here. And then finally, when the flow hits in a static fashion, you have the typical weld lines in your part. And so this is exactly the critical areas, the flow lines and weld lines that you like to reproduce when going to a coupled analysis. And coupled analysis, how does this work? So the base input, the base information is really your processing simulation, so it's injection molding. And you get the fiber orientation distributed on your injection molding mesh. Then what you typically have is some measurement lying around. So in the easiest case, you have a measurement of an ISO 527 dumbbell with quite some high alignment of fibers in this dumbbell, or you even have anisotropic measurement, whatever it is. And in the classical approach, you apply it in terms of an isotropic material model to your FEA, to your structural analysis. And here we see, for example, a resulting failure pattern for the case of the isotropic material. And now if we turn to the coupled approach, these isolated islands will be combined. And how do we do that? Well, first, we set up, based on the measurements, a material model which is anisotropic, and typically it is nonlinear because short fiber reinforced plastics exhibit a nonlinear mechanical answer or response in the tensile test. So this we have, and now the task is to couple this locally to correct information about the fiber alignment. And this requires a mapping step because the injection molding mesh differs from the structural mesh. So locally distributed after mapping on the structural mesh, you will have your fiber orientation. You can feed this fiber orientation into a material model, put that to your structural analysis. So the Digimat material model is connected to your FEA solver via a user subroutine and interactively communicates with the FEA solver for the material properties. And then if we look at the right side of this slide, if we look at the failure pattern and we turn to anisotropic, we see that we have really a great change here in the material response locally, and this is based on the local fiber orientation. So this is a coupled analysis, and if we now want to state briefly what it brings to us, well, all the critical regions like flow lines and weld lines, which I have mentioned before, will be highlighted automatically in your analysis because they are introduced via the microstructure, which is underlying in the material. So especially the nonlinear modeling gives you the advantage that as a result you can, for example, plot the plasticity in your material matrix. And this is what we see here on this blue tensile bar. And the critical region, the static weld line, is highlighted in red because the plasticity really accumulates in the matrix in this critical local region. And this automatically happens when you switch to coupled analysis. So if we take a deeper look into the material properties that we like to cover, I want to put up a list of first-order effects of short fiber reinforced plastics. So asking the question, what kind of material performances do we need to cover? And it really starts, and we have seen that on the previous slides, with the anisotropy of the material. So this is depicted on the right upper corner in this slide. For the BOM material, you have this spread of material properties between the aligned and the transversal state of the fibers, and this is absolutely critical to take that into account individually, locally on each integration point. Then, if you turn to nonlinear description of the material, it's very critical to do that, to cover the real response of your plastics. And this will automatically highlight the flow and the weld lines. This is what we have discussed on the previous slide. But then we can even go further. We can say, what are the next critical influences? And this is definitely temperature dependency. And we offer temperature dependent material models. So if you think about under the hood type of applications, for example, you could set up a thermomechanical coupled analysis with Digimat model, which are fully sensitive to the local temperature, at the same time taking into account the local fiber orientation. Next step, and this is about thinking about impact scenarios, is that you take into account strain rate dependency. And of course, you need, for explicit type of analysis, a good description of the failure of the short fiber reinforced plastics. And this we can do. So we combine an elastoviscoplastic material model, for example, with a good failure description for short fiber reinforced plastics. Again, turning to strain rate dependency, what we also can do is we can go into the regime of extremely low strain rates, which is then talking about creep of material. And here it's again interesting to couple that with temperature effects. So what we offer is material models covering temperature-dependent creep. Here's some example where you end up in terms of correlation with experimental results. And for this part from Schneider Electric, we see a comparison of a PBT material, glass fiber reinforced with 20% fibers on the left side and 50% fibers on the right side. And you have here the typical comparison between some isotropic material model, which is in black, the experiment, which is depicted in red, and our Digimat material, which is depicted in blue. And you see, if you turn to the Digimat material, for both types of material in this part, we have perfect match with the experiment, and you have a large deviation if you apply some isotropic material model. Here, the material properties along the fibers were taken in the simulation. We later see some other comparison where another scaling factor was used, but anyway, scaling factor, one doesn't know which one to use. I'll explain later on where we stand there. With Digimat, you always have good match with your experimental results. So other successful applications, this slide is supposed to give you an overview in what kind of areas we are. So it starts really with NVH, so taking local linear elastic material properties into account, like in this front end here. Then we turn to stiffness, quasi-static stiffness. Here, the typical application would be with a nonlinear, so elastoplastic material model, also in combination with temperature dependency. Then we can turn to impact and failure, so that would be the elastoviscoplastic material model, strain rate dependency, strain rate dependent failure model also. We have nice results on engine mount here in a collaboration with between Rodier and Trelleborg. And as I mentioned, thermal creep, so that can be described viscoelastic or elastoviscoplastic. And the typical application would here be the oil pan from General Motors, so a typical under the hood type of application. This is to give you an idea where we stand. And of course, now we are curious about how we do that. What is the approach to material modeling that we take? What we do is that we apply a module that we call Digimat MF. And MF in that name stands for mean field homogenization technology. So what's there behind is mean field homogenization. And this requires the input of separate material properties for the matrix material and the filler material, together with some additional input about the material microstructure. This input we take and we perform the homogenization step, and basically this results in the typical Digimat material card, as we can see it here on the right side of the slide. So we have discussed it previously already. It's basically a sensitivity of nonlinear material behavior towards the fiber orientation. So how do we do that more in depth? As I said, you need to assign material properties to your matrix phase and your fibers phase. Typically, nonlinear behavior, strain rate dependent behavior, and so on and so forth is taken into account in the matrix properties of your composite. Then further on, you need to define your microstructure, and this is starting with a matrix, which is the background basically, and in this background you embed the fiber as some ellipsoid. So all these technologies based on the approach of Eshelby. That's quite an old one. It was enhanced to the Mori-Tanaka for nonlinear material response, and all that we have in the software takes Mori-Tanaka as a base. So you define fibers in terms of their shape, an ellipsoidal shape in terms of an aspect ratio. Of course, you need to input the percentage of fiber reinforcement that you want to tackle, and then you go for the orientation. The orientation can be defined via some orientation tensor. describing the random or the probability of finding alignment of fiber in different spatial directions. And this is exactly the output that we get also from injection molding simulation. So here is where we close the loop towards the processing simulation. Even further into depth, what we do is we do stepwise homogenization procedures. So it starts in the middle of this slide with some, and this would be a three-phase material here consisting of, let's call them black fibers or fillers and white fillers in a material matrix. And the orientation tensor describes a random distribution of these fillers. First step that we do is on the microscopic level, that we decompose all these fillers into specific classes. And each class is a representation of a specific orientation of the filler. And this we do for the black fillers, for the white fillers. And now we can say each of these classes, we give them a name, and we name them pseudo-grains. And for each pseudo-grain, we now perform a homogenization step. And now we're at the bottom of the slide. We will have for each pseudo-grain now a specific stress state, a stress state and a specific fiber orientation. And we can compute the material response from that. In the final step, and this brings us then completely to the microscopic level and to the average material properties, we average the material response between all pseudo-grains. And this is a very important procedure here because our implementation of failure, so via the FPGF model, first pseudo-grain failure model in Digimat, is exactly on this pseudo-grain level of material. I'll highlight that a bit later on. So this is the theory behind. Let's now look what we find in terms of measurements, because we of course need to parameterize our material model somehow, and this is performed by some reverse engineering procedure to some underlying experimental curve. And here we have two types. First type would be the typical ISO 527 dumbbell, which is directly injection molded and which exhibits a high stiffness, so it's the red curve here in this diagram, due to a high state of fiber alignment in the dumbbell. Or we can injection mold a plate, and this has the advantage that we now can cut in different angles with respect to the main fiber direction, so flow direction in the plate. So 0, 45, 90, for example. In this diagram, you see for 0 degree the green curve and for 90 degree the blue curve. And you can see also what happens. Well, if you go along the main fiber direction, you have quite a stiff response of your material. Of course, if you go transversal, you have a lower stiffness. And now it has some relation between each other. So ISO 527 is the stiffest possible response, I would say, in the typical measurement. Then you get long from injection molded plate as the next one, and the lowest stiffness you get in the transversal measurement from the injection molded plate. So these are the typical base measurements that we start from. And what you can do, you can first say, okay, I only have an ISO 527 measurements. This can readily be found also in material databases. So you wouldn't, in principle, need to perform your own measurements. It's readily available. Campus is a good example for a public database. And you say, I want to go for a non-expert, quick and easy way of reverse engineering my material model. And so this is relying only on one curve, so on the red curve here, and gives some input to the microstructure which comes from experience. So what you end up with is a material model, and this fits very well the red curve, so the ISO 527, and then you can take this model and recompute the response you would get for the dumbbells from the injection molded plate. And what we see is not surprising. So the green curve is matched still quite well because you still have a high alignment of fibers. But if you go to the complete transversal state, it shows deviation from the experimental measurement. And this is, of course, because we only took high aligned state of fibers for reverse engineering for parameterizing our model here. So, but still, it's a way of creating in a very quick and convenient style material models in Digimat, and we'll see later on where we end up with that kind of approach. So this I want to call semi-quantitative material model. Of course, you will want to have more, and this will bring us to the quantitative approach to modeling. Quantitative modeling means that you have really the full set of material measurements, so different angles cut off from injection molded plate. And you also seek more than just the simple nonlinear stiffness of your material. So, for example, you want to have a global match of your stiffness together with a global match of your failure behavior in your material. So if you want to incorporate failure and get the global stiffness, this is definitely the task of quantitative modeling, and this requires expert work because you have to look into detail in the microstructure, validate properly, and so on and so forth. So of course there is an effort that you put into it, but the resulting material models of the highest possible quality and are really state-of-the-art what you can do in terms of modeling of short fiber reinforced plastics. So turning to failure that I pointed out, we have some specific model here in Digimat. I think it's quite unique on the market. It's the FPGF model for first pseudo-grain failure. And what's behind it is basically that if you turn to this pseudo-grain level that I have described before, you find that in each pseudo-grain you have a local axis system perfectly aligned with your fibers. And this is in the situation similar to a micro laminate, and for laminates there are many different failure indicators that you can use. And our typical approach is here that we take a Zi-Hill 3D transversely isotropic stress or strain-based failure indicator, and we use it in reverse engineering of our short fiber reinforced plastics. And what we see then is that the failure behavior can really mirror what we find in the experiment. And this means that if you go to a high alignment of the fibers, so the green curve, the stiffest green curve here, you have a very stiff and brittle behavior of your material. And if you now turn towards transversal direction with respect to the fiber, you turn to a material behavior which is low in stiffness and ductile in its failure behavior. And this kind of stuff we can mirror in our material models if you do quantitative modeling. Here is some example what that means for the failure behavior, and it basically shows in a movie what we have seen before. So if you look at the left side of this slide here, we see the movie for the failure for some isotropic material. Basically, you see two parts flying away, and the failure here is induced by the local stresses and strains in your material, but they come basically from the geometry of the part here. Whereas if we turn to the failure behavior with an anisotropic model, we see completely different behavior, and this is taking into account the local fiber orientation. And if you just imagine what this means for an impact scenario, if we just want to discuss energy absorption and everything like that, you see the implication. It's definitely important to get the description right. So now we have understood a bit what we do in terms of material modeling, but we still haven't seen how to apply it in different simulation strategies. And we can start talking about design stages and so on, and the number of designs that you will want to look at. And it's very easy for the late stage of design. You have only 2 or 3 designs. You want to investigate them really into depth, and this is an expert stuff. So the expert will look into the local microstructure, so on, do the full quantitative Digimat approach, and even will want to take it on the system level of computation. So, for example, going for full car crash. And of course, because this is expert stuff, it means you will have to do a real quantitative approach. It gives you the state-of-the-art in material modeling. It gives you a very high quality of results, the highest possible. But of course, and this is also true, the effort to build such a material model is also quite high. So you cannot do that every day. You just do it for separate and isolated cases. There is effort in building the material model, but also, of course, there is an effort in the computation. So if we turn for explicit, for example, you will have some additional cost in your CPU. I will discuss that a little bit later for an applied example. What it basically means to a company is that the company needs to invest in manpower, or somewhere the manpower of this expert material modeling will have to be located. So either you join in with a material expert, can be us as Extrem Engineering, it can be your material supplier even, because we facilitate in an easy way via Digimat MF, our material exchange platform, the communication with your material expert sitting on the material supplier side. Or you can, of course, build the material expertise in your own company. But this requires someone dedicating to Digimat. Now, if we turn to the early design, what we see here is that, of course, a large number of designs have to be tested. And today, people use the classical approach, means it's based on isotropic material properties. And it's reduced, of course, to the part level. Suddenly you find system level simulations here. And now, if we discuss what is used today and the isotropic material properties, it means that the isotropic material properties are basically a scaled curve for some type of measurement. And here in the upper right, we again see our typical 3 measurements. And the question is really, which is the correct scaling factor of what curve? So what do I use? And the answer is no one knows. Scaling factors are not unique. They depend on the geometry, on the material itself, on the injection process behind, and also loading condition. And this is the interesting thing that seldomly someone knows. We see on this slide the example for a global load and a local load for the same part, same processing, same material. And we see that the experiment is reproduced in the blue curves on the left side with a scaling factor of 0.76, whereas on the right side for the local loading, you need a scaling factor of 0.6 to reproduce your experimental curve. So it's really a vast difference in the scaling factor, and by no means this is a unique one. So you don't know basically which one to use. If we then turn to the Digimat model, and this is the black straight line, it matches the dotted black line, which is the experiment in both cases, but with a unique description of your material. And this is very important because it introduces a measure of certainty to your simulation. And so what we need now for the early design stage is the semi-quantitative modeling that I have discussed before. Semi-quantitative modeling, of course, does not cover the full effect in a material, but it gives you a part of the possible state of the art in material modeling. It increases already hugely the quality of your results, but in terms of effort to produce such a material model, to set it up, it's quite all right. A non-expert can do that, really. And we have improved with the 4.4 upcoming version of Digimat, so we release it in April. We have improved the workflows a lot here, and we offer possibility for a non-expert to set up micromechanical models and to use them right away. And this means for the company again, the invest of manpower is really low. The same guy performing the FEA analysis in the past can do the coupled analysis today. There's really nothing that is really complex about this setup here, but it introduces via the coupled analysis a high level of certainty. So the measure of uncertainty is really reduced here in your simulation approach. This can be used in the early design stage. A bit how we improve the workflow for that. So what we offer with the new version of Digimat is generic material models. Generic in a sense that we build families of typical grades. So a typical grade would be, for example, a PBT GF10, a PBT GF30 or GF50. And now we collected all the data from different material suppliers, we averaged them, and we just reverse engineered a material response to this average. And this is what I want to call a qualitative approach to modeling. The advantage is these material models can be used right away. So you just click them, use them, and you get your results. How can you improve that? We can combine this approach with what is available in public data. And if we look at these data, it's again ISO 527 measurements, but you can have different and many information here. So this is for dry and conditioned type of measurements at many temperatures. It covers many different grades. A broad range of reinforcement can be found here, so on and so forth. So you can go to a database. You take the individual curve, mirroring what you get from your material supplier, and then you just reverse engineer your semi-quantitative model. And this semi-quantitative model is really only 5 minutes of non-expert work, so just loading in a curve and a bit tweaking the material properties that the generic model then fits your individual model coming from public database, or of course your own measurement from that you have performed. So again, for this model, do not overestimate the quality of the model. It has this deviation when you go transversal to the fibers, yes, but again, do not underestimate the benefit of its usage for the early design stage. And actually, in the practical application, the example that I have shown you before, this perfect match here between the experiment and the Digimat model was already based on such a kind of semi-quantitative modeling approach. So we have tested different customer examples, and the outcome is that with a qualitative, so a generic model, you will end up with about plus minus 20% deviation of experiment maybe. Then with semi-quantitative, you can hit on the spot like here, but a typical expectation would be a plus minus 10% deviation from the experiment, whereas with the quantitative modeling, of course, you expect a very good match because you're doing really state-of-the-art. So with quantitatives, you're always sure that you do the best that you could do. So these are the different simulation strategies that we cover. And now let's turn to some application examples, and this would be first the story of our full car crash. Why is this a very interesting story? Because it tells at the same time the story about the development of our hybrid solution approach. What is this again? So for explicit simulation, if you take the homogenization approach, so micromechanical material modeling as a description of your material in your integration point, and you run a coupled analysis and you compute on-the-fly material properties, you can imagine that if you do that in explicit for each integration point, for each time step, this is a very costly thing. And this showed when we turned to the part level and we had a typical impact scenario like we see it on the left side of this slide. It took then in explicit solution 9 days to solve. It's possible, but it's for sure not something you would repeat very often, and you want to induce in a typical design cycle and definitely not for an early design. So we became aware of that. That was already 2 or 3 years ago. And what we did is that we thought about an approximate solution, which we call the hybrid solution, which has we had the idea to turn really to system level. So our goal was to go to a full car crash incorporating a fiber reinforced plastics. And we invented that new method of describing things, basically reducing the amount of communication between Digimat and the FEA solver, performing a pre-processing of material properties and so on and so forth. So there are details to the story. But what it brought to us is it reduced our computational time from 9 days to 8 hours. And 9 days was a computation on 3 CPUs and 8 hours same on 3 CPUs. This hybrid solution, of course, has been tested. So what we did is we compared a lot between the micro, so the most correct approach, and the approximate, the hybrid approach. And we found a really nice correlation between the global response of our examples, so what we see for this example on the left side of the slide, and the local response in terms of stress and strains and so on distributed of the part as we can see it on the right side of the slide. Again, it brought us a tremendous speed up. So we computed this example here, 9 days, 3 CPUs, 1 day on 1 CPU. And of course, parallelization in this regime of CPUs goes linear with Digimat. So you can say that was 8 hours on 3 CPUs. So really good success. And then we had a very, very nice story on the users meeting when JSOL, our Japanese reseller, who at the same time are resellers of LF Dyna, just tested this approach for full car crash scenario. And what they did is they described an injection molded part in an overall system of 3.1 million elements. Digimat was represented by only 1% of all the elements, so roughly 30,000 elements. And and they combined the hybrid solution approach with some clever way of parallelization, so basically tweaking the domains in parallelization in LS-DYNA at the same time. So two means of improving CPU. One would be introduction of Digimat hybrid solution. The other would be a change in the domain separation upon parallelization. And now if we go to the comparison of CPU time for 32 cores, we see that the isotropic model runs in roughly 9 hours. And if we now turn to the hybrid method, we see that this CPU time or the CPU time increases to 42 hours. You see that hybrid alone is not the solution here. So 42 hours is still quite some long time. And the goal, the metric here was to compute in the same time as for the isotropic. But then if you introduce hybrid solution together with the domain separation, you end up with 14 hours of computational time. So we are definitely in the right direction. And now you can say, okay, I optimize my model and so on. You can still gain some time. But of course, there are means that you just say, okay, from 14 hours, if I use double CPU, where do I end up? And you see that we end up for a full coupled analysis in 8 hours. And just for you to compare, if you take the micro approach, also with decomposition in different domains, you will compute for 152 hours, so 6 days, roughly 1 week. And with a hybrid solution and domain separation on 64 cores, we can do it in 8 hours, absolutely comparing to what you can do on the isotropic side. So real good success, and really we have reached now the system level that we can apply in a practical style the coupled simulation. Here we again see what you get from it. So it's really different stress patterns locally due to local fiber distribution, different failure behavior due to a more correct description in your anisotropic model. So this was a very nice success story. Another story about the advantages of going for Digimat is that Digimat is a composite modeling platform. Also in the automotive context, what you find more and more is the idea to create complex composite designs. So people do not only want to stay with short fiber reinforced plastics, but you find hybrid solutions where the part is a hybrid composite part made of woven composite, so organo sheet overmolded with some features which are a thermoplast with short fibers in it. And with Digimat, you can describe both the woven composite and the short fiber reinforced plastic with the same modeling approach. And this is what I want to show you here. So on this slide, we see a reverse engineering result for the short fiber reinforced plastic. So this is now for dumbbells, again, cut out of an injection molded plate. So really nice correlation here. You can do the same if you turn So this is now for the material model. On this slide, we see the correlation computed really in a coupled analysis on the dumbbell level. And if we turn to the woven composite, you can do the same. So here you see reverse engineering of material properties on the integration point for the woven. Experimental measurements are again here 0 and 45 degree with respect to the woven pattern. And if you go to the correlation with experiment again for the test specimen, again perfect match. So now you can compute for a hybrid part a different design between a purely short fiber reinforced plastic part. So this would be the blue curve. And the hybrid design, so the new design, which incorporates woven, so organo sheet, as well as the short fiber reinforced plastics. And you see that you end up with about a double in stiffness response of this part, so very much improved material properties. And especially for these new types of scenarios where we don't know yet where we will go in the future, and it's important to be able to cover many, many different composite materials in one overall simulation approach to really be able to go for virtual design. Digimat offers real advantages because it's a modeling platform in a generic sense for composite materials. So this is the end of the story in terms of application examples. Let's now look a little bit more into the future even by discussing the fatigue topic. And Digimat fatigue, what does it mean? Well, If we discuss lifetime prediction, the first step that you have to get right is the correct stress input into your lifetime prediction software. And this again means correct local stresses can only be computed taking into account the local anisotropic material properties. So everything that I have shown before is already 50% of the improvement of the lifetime prediction here. So correct local stress states we put into the fatigue level, so lifetime prediction software, but then there is the other story to it. Again, for the lifetime prediction, there are different measurements that we have. These measurements would be now Wöhler curves, so SN type of curves, which also are anisotropic, so they depend on the local fiber orientation. And we take exactly the same simulation approach as we have seen it for the stiffness, and we map the local orientation onto the structural mesh, and locally then we decide which SN curve to take from our fatigue model, and the fatigue model is derived from our measurements, and this is fed into the lifetime prediction software. Now, what kind of fatigue models do we offer? First one that we have is a pseudograin-based model. So it incorporates the idea of the pseudograins again, so on and so forth, but basically what it does is you input measurements of your SN curves, which are anisotropic, and the material model can intra and extrapolate based on micromechanics the response for the unknown fiber orientation. So this model is definitely a good model to start with for short fiber reinforced plastic. Then we have another model which enters the software with a new version. It's the matrix-based model. And this is especially interesting because it offers the possibility to reverse engineer matrix properties. Fatigue is then incorporated in the behavior of the material matrix, so really on the microscopic level. And you can remix different amount of fiber into this matrix, and this means you can predict now, depending on the percentage of fibers, the fatigue properties of your Wöhler curves. All this we put into interfaces to lifetime prediction software, and where we stand today is that we offer interface to LMS virtual durability to HBM encode, and what we will finalize this year still is the interface to FEMFAT software. So this brings us to Digimat software, the last topic I want to present a bit today. So modules and solution. Digimat is always comes in a modular style, so it will be a combination of different modules that you will use in your individual Digimat solution. If we talk about short fiber reinforced plastics, we can simplify all that a little bit. So here is a comparison what module you use on what level of our multiscale modeling approach. Digimat MF, as I told you, is the base technology, mean field homogenization. It's used for really setting up material models on the microscopic level. So you can say Digimat MF is our virtual material. And then you turn it to structural engineering by using Digimat MX. MX stands for Material Exchange Platform. And what you can do here is you can load in experimental curves. You can reverse engineer, so parameterize your Digimat material model by using it. And then you put it to the interfaces, which are combined in Digimat CAE. Digimat CAE would mean, for example, that you take a Digimat CAE interface to Mark software, to Nastran software, or and you add a Digimat CAE interface to Moldflow to be able to read in your processing simulation data. And as we have seen in the overall approach, of course, this you combine with a mapping tool, and this is what we offer with the Digimat map module. So this is how the approach is built in terms of the modules. Talking about the environment of your simulation, what we also offer is plugins to specific environments. So a plugin is used that the FEA engineer doesn't have to leave his most beloved CAE environment. So the plugin can call directly Digimat. It leads you through the overall process of building a coupled analysis very easily. We just recently incorporated Mark Mentat in this overall approach. So this is available. And in the end, you come up with a complex table, as you can see it here. But basically, what is the message of this table? The message is that because we have a modular approach to setting up the customer solution, you can really start with the simplest analysis. So the simplest would be Digimat linear solutions. And it's really a non-costly solution. You're right away in the story of coupled analysis, and you can build from there. We really offer a ladder how you can develop from a designer state, the simple state of coupled analysis, into some expert state. And this is by just adding modules and functionality. So you start with linear elastic. You may decide to enhance your approach on the material side, going for nonlinear. You may want to add more mapping capabilities and so on and so forth. And finally, if you then, in the end, add Digimat MF as a full expert solution to composites modeling, you're really at the highest level that you can get. But step by step, we can lead you there, and the software is built for an easy access to the overall topic. And this basically brings me to the end of what I wanted to tell you today. So my summary slide really reduces things to that level. So again, we offer a solution on the designer level. Designer level for me would be based on public available data, so ISO 527 type of measurements. It would already cover effects like nonlinear, stiffness, plus temperature influence. We offer here the qualitative approach to modeling via the generic materials, and they can very easily be enhanced for individual material measurements in a semi-quantitative style. Then the next level is really the expert level. So this is basing on isotropic measurements, and this covers all the advanced performances that you can find. So failure, dynamic behavior, creep behavior of your material, and if we look into the future, also the fatigue of short fiber reinforced plastics. And this is what I call really a quantitative approach to material modeling. So it's really material models for the individual need of our customers. This brings me to the end. I thank you a lot for your attention, for joining today's webinar. And with this, I'm open for all of your questions. Thanks a lot.